And this is 9-2, the alpha lesson. So here's a question from the end. From 39, just read the question. You can't do this question yet. Just read it so you know what to anticipate. And we're going to go here. We're going to go to exploration 1, which is in the textbook on page 484. You want to build a polynomial, okay, that has this behavior at 0. The function has a value of 1. The first derivative is 2. The second derivative is 3. The third derivative is 4. And the fourth derivative is 5. So take a couple moments and try and see if you could build something, right? Now, you understand what they did here? They wrote this polynomial backwards to make it easier for you to build it. So you put the constant first, and then the exponents are going up from left to right. It doesn't matter. Okay, but that's the way they organize this. So, you know, this is b sub 0. This thing's going to be a 1. The constant's going to be a 1. But then you need the first derivative to be a 2, the second derivative to be a 3. So you're going to look at that for a few moments, and we're going to go over what that would look like. Okay? All right. You might not have finished it, but you got to get a start on it. So it would look like this. We have the 1's the constant, yes. And the derivative, the first derivative at 0 is 2. So when you differentiate this, you would get 0 plus 2x of the derivative, 2x, you get 2. And then as you expanded it, you would get here, as you went to the next terms, okay? But now we're going to organize this and say, okay, well, I can rewrite 1 as 1 over 1. I write 2x as 2 over 1 times x, and then write the exponents in here. So I'm going to write this as x to the 0. Anything to 0 power is 1. So this is 1 times x to the 0 plus 2 times x to the first, 3 times x squared, 4 times x cubed, 5 times x to the fourth in the numerators. In the denominator, well, 0 factorial by definition is 1. 1 factorial, 2 factorial, 3 factorial, 4 factorial. So what do you notice here? That what you did here, this is the general form. Right? This is a Maclaurin series. This is a big deal. Right? This third line right here is your ticket to success on the Chapter 9 questions on the AP test. Any function can be approximated with this series, which is what? You take the value of the function at 0, the value of the first derivative at 0, the value of the second derivative at 0, the value of the third derivative at 0, the value of the fourth derivative at 0, and they're in the numerator. And the denominators are 0 factorial through as many terms as you go, and the powers are x to the 0 through as many powers as you go. Okay, so we're going to go to the PowerPoint. And this is the next problem. I wanted to go over that first because this is the next example in the book. So you want a 4th degree polynomial. So they're telling you how far to go. You want the function to be ln x plus 1 at 0. Okay, the at 0 doesn't make sense yet, but don't worry about that. So we do this. You put 0 in the function, and it gives you ln1, which is 0, which makes your leading coefficient 0. You differentiate natural log of x plus 1. You put 0 in the derivative. Ready? And you have 1 over 1. So you're getting a 1 as the coefficient of the x term. You differentiate, take the second derivative, which is the power rule. You have 1 plus x to the negative 1. D mu is 1, so you have to worry about that. Put 0 in there, and you get a negative 1. Except what? Except you would have, when you differentiate this, you'd have 2a to the second, x to the first, and you differentiate again, you just have 2 times a to the second. So 2 times this coefficient equals negative 1. So this coefficient would be negative 1/2. You didn't notice that the first time. Why? Because you had a constant. And then when you took the derivative, the exponent was 1. So you had 1 times a to the first. Now, because you had this exponent that was other than 1, you're not just taking the value of the derivative at 0. You're setting this equal to the value of the derivative at 0. Third derivative gives you 2. So 6 times that coefficient has to equal 2. So it has to be 2/6. Fourth derivative, (24) times that coefficient has to be negative 6, so it's negative 6/24. So here's your 4th degree polynomial to approximate ln1 plus x. And you're just reducing the fractions. So what's happening here? P is in red. I'm sorry, P's in, the power series is in red. The function's in blue. So in the interval, it maps right onto it. Or very right onto it, very close to it. And if you zoom in, you see the same thing. Okay? And this is not where I like what is on the PDF better than what's on the PowerPoint. Because what they did here, what we did on the PDF, which is going to be helpful to you, is we put this f sub 0 over 0 factorial times x to the 0. This f prime of 0 over 1 factorial times x to the first. So you can see the pattern. This isn't as helpful as what's on the PDF. There it is. Okay? That's a big deal. Ready? You cannot succeed without this. And it's a user-friendly pattern. So the Maclaurin series, and again, this is not the best way to write it. The best way to write it is to put the 0 factorial under here times x to the 0, the 1 factorial under here, and give this x an exponent of 1 so you can see this pattern. That's a Maclaurin series. Maclaurin is subset of Taylor series. So Taylor series is, well, it doesn't have to be 0. It could be a, some other value. So if you put in some number other than 0, what are you doing with the x's? You're doing the opposite. So you're shifting it a units to the right by doing the opposite and substituting that value other than 0 into the function of the derivatives. So how about cosine? So we want to see if we can write a power series to estimate the cosine wave. So if you put 0 in for cosine, you get a 1. Derivative cosine is negative sine. At 0, it's a 0. Derivative negative sine is negative cosine. At 0, that's a 1. The opposite, that's a negative 1. Third derivative, going to give you a 0. Fourth derivative, you can't see this, well, I guess I'll move this, but it's going to give you a 1. And you're going to see this pattern. So what do? We see that every other term is 0. Yes? So you're getting 1, which in effect is what? 1x to the 0. And then you're getting the even exponents over the even factorials. And the signs are alternating. Well, hopefully this makes sense to you that you can make this connection. The cosine is an even function. That's its symmetry. So there's the cosine wave. Look, this is pretty neat, the way they do this. As they're progressing here, you're seeing how, as you add terms to this, you're seeing how much more closely P of x maps onto the cosine of x. Okay. How about cosine 2x? Well, the issue is you don't have to start over again. It would still work. You can just put 2x into the expansion of the cosine. Well, that's helpful. So how about if we shifted it from Maclaurin to Taylor? We want to put it around pi over 2 instead of 0. Ready? Because you shifted it to pi over 2, the initial term was 0. Here's the signs alternating. And you've got, instead of an x, you have x subtract pi over 2 because you're moving it pi over 2 to the right. And then what happened? Well, you lose the symmetry here if you're centering this about pi over 2. So now you have the odd powers. Yeah, that's true. You're going to have to. We're going to go over that with you on the PDF, and then the distinction here between terms, order, and degree. Yes, 3 terms. I see that. Fourth order. Fourth degree. But the third order, because that third derivative is giving you a 0, this thing is third order, but it's just degree 2. Because you kept going plus 0. So that's the distinction they're making there. The degree and the order aren't necessarily the same. Okay. So back to the PDF. You are accountable for these. E to the x, we didn't get to this yet, but e to the x, sine x, cosine x, and this one which we've been doing, which is a geometric series where the constant multiplier is x. You need to know these expansions. You don't have time on May 24th to be building these expansions. So here's how we did what was on the PowerPoint was cosine x, so here's sine x. So I said, okay, ready? If you put 0 in for the sine is your y, you would get a 0. Derivative of sine is cosine. Cosine of 0 is 1. And then it's the same thing. Once you get to 0, 1, you know these numbers are going to just repeat. So here's my 7th order expansion. Right? And I started with leaving the zeros in here, and then I left them out for the 4th and 6th. Because it's the sine wave, and the sine wave is, see, this thing is 0, and that's a 0. I didn't write the zeros for 4 and 6. And the sine is an odd function, that's its symmetry. And you notice what you have. You have the odd exponents, and you have the odd factorials. And then the general term. Here's how we write the signs alternating. -1 caret n, if I start at the 0 term. 2n plus 1 is an odd number because 2n is an even number. No matter what n is, you double it's even. So you could write this as 2n plus 1 over 2n factorial. It's telling you it's all these numbers in the denominator that you're multiplying by themselves are odd. Okay, and then this is not the only way to write this. Okay, you could say I want to write n equals 1. Then these terms would be different. It's not just one correct way. You just have to make it balance. So we're going to pause the video and ask you to go to problem number 3. Okay. What happened? Well, here's the function. So I put 0 in there, I get 1/2. I put 0 in the derivative, you get -1/4. You put 0 in the second derivative, you get +1/4, and so on. So you just get down here and you paste those as coefficients. The 1/2, -1/4, 1/4 over 0 factorial, 1 factorial, 2 factorial times x to the 0, x to the first, x to the second. So you clean it up a little bit, and you would end up with 1/2, take away x over 4 plus x squared over 8. If you only got that far, that's fine. You generalize that, right? Whenever the signs are alternating, -1 to the n, if you start at n equals 0, the first term were positive, x to the n. So this is, ready? -1 to the 0 power is 1. I have 1 x to the 0. So that's 1 times what? Denominator is 2 to the n plus 1. 0 plus 1 is 1. So I have 1/2 x to the 0. So that's how we interpret the general term. And if you see what's happening, the denominators are powers of 2. And the x's are just arithmetic. All right? So the thing that would be helpful is you could take anything. Like you could take any polynomial. You don't even need to do this. Like just take some user-friendly cubic and do this to the cubic. You'll get back to the original problem. And we'll do something like that. It's kind of more visual. Do it when we get back in the building, but you can certainly practice it. This is a big deal, okay? Maclaurin is a subset of Taylor. Maclaurin's based around 0. That's how you're going to begin doing this. And you're just substituting in this expansion right here. Right here in this bottom line of that box. It's not complicated. You need to get your mind around it to build anything. And then additionally, you're going to memorize a few of these.